Alright guys, so welcome back. This is part 2 of basic protein components as a component of food, but we need to understand a little bit about the biochemistry of protein, and the most important biochemistry is the protein structure. There are 4 hierarchy here, starting from the lowest, the primary. This is just the backbone of the polypeptide chain, followed by the folding of the polypeptide backbones or localized backbones. This is called secondary structure. And then we go to the tertiary and the quaternary structure, where we have the actual functional forms of the protein. Okay, and as we go from primary to secondary, tertiary, and quaternary, you can expect the structure to become more and more complex. Okay, we start with the primary structure. This is just, I said before, just a sequence of amino acids, polypeptide chain. Normally we can use 3 letter codes to denote the sequence. In this particular example is given there: alanine, ALA, and then glycine, valine, etc. Okay, the key point from this is like the backbone structure, that whatever constitute this long chain of polypeptides. This structure will dictate the rest of the protein structure. So from the primary, it will soon become secondary, tertiary, and then quaternary. So the primary structure will dictate the rest of the protein structure. That's what it means. Why? Because of this identity of all the side chains, the functional groups that coming out from that amino acids, and then the sequence, the order they are arranged, will determine how a protein will fold up, and how this protein fold up will determine the protein functions. Okay, all right, so that's the primary structure. The secondary structure, we are getting more and more complicated or complex. This is the long polypeptides are now starting to fold. So secondary structure is about the folding pattern that a particular protein will exhibit over a few dozens of amino acid residues. Alright, so there are 2 types of secondary structure that is most common. There are many, 1 or 2 others, but alpha helix here and then beta sheets are the most common secondary structure. It is characterized by the key point is, for the secondary structure, it is characterized by the internal hydrogen bonds. You see there, indicated by the arrow, that is the hydrogen bond, internal hydrogen bond. That's for alpha helix. For beta sheet, same thing, you can see the internal hydrogen bond. It is this internal hydrogen bond that form between adjacent amino acids, say this amino acid and that amino acid, considered adjacent in one particular sequence. Because of that, you cause the alterations or the folding of the whole polypeptide chains. Remember, there was no folding before. It was just one line. Suddenly, because of this internal hydrogen bond, it becomes folded. Okay, all right, so same thing with the beta sheet. This is this backbone, like we mentioned in the primary structure. This backbone extend one way and suddenly it make a turn back to the line up alongside of the first. This is the first part of the chain, and all of this because of the formation of the hydrogen bond. Okay, so looks complex, but we don't have to know the detail, because for our level we just need to know existence of the secondary structure, and there are two types that's mostly common: alpha helix and beta sheet. So as mentioned, initially there was just one polypeptide backbone. Suddenly adjacent amino acid here, and then another amino acid there. They have decided to form a hydrogen bond, or internal hydrogen bond. I'm going to label that. Okay, so because of this internal hydrogen bond multiplied by, say, thousands of, maybe another thousand, several thousands of internal hydrogen bond, you cause the alteration of the structure. It become more coil, therefore the alpha helix structure. Yeah, so that is the hydrogen bond being formed there, and then you can imagine you have more and more, a lot more. Okay, so from the primary structure, because of this folding state, tada, we form the secondary structure of protein. Okay, but at this level the protein is not yet useful, it's not yet functional, it is just structure. Well, you can find books explaining, showing a nice diagram there of alpha helix versus beta sheet. See the sheet there, making it look like a wavy rather than spiral helix nature. Okay, next we are ready to go to the tertiary structure. Okay, now after folding in the secondary structure, in the tertiary structure, we are still folding, but now we are into 3D, yeah, three-dimensional conformation of structure. In other words, we are approaching a complete folding pattern to yield the overall three-dimensional structure. Many proteins, such as many globular proteins, collagen, this is the final structure. Yeah. How the types of the structure is normally dictated by the sequence of amino acids, as mentioned before in the primary structure, and then whether it is formed via alpha helix or beta sheet involved there, and the stabilizing forces involved, like maybe disulfides or hydrogen bonds. Okay, no details. So this is just I'm trying to depict, imagine that would be the alpha helix over here. Can you see the alpha helix structure there? Oops. Okay. And then we have can you see the beta sheet? Yes. All right, so they come together to complete the folding pattern. Yeah. All right, so you want to be simple about it. It is a secondary structure folding into three-dimensional conformations. Okay, a little bit more on the tertiary structure. You see the folding of this protein. It looks random. It appears random, but it is not. Our body knows what they are doing. Yeah, the folding via intra happening inside, and then interlinked polypeptides is very specific to the protein. It will occur in that specific way every time that particular protein is formed. Our body really know what they're doing, and this particular shape gives the protein its function. It is important for the protein to form the similar function in order for it to become functional. Yeah. Okay, I don't know who to ask this question. Why do protein undergo folding? Well, that's the natural part of it, of our body biochemistry. But scientifically, is to bury the hydrophobic amino acids primarily on the inside and expose the hydrophilic groups on the outside. So the reason for folding is to bury. Any example of functional proteins with this structure? Yes, maybe you heard about globular protein, which is highly folded and compact. So you can imagine like a ball of globular proteins. Egg albumin are a good example. There are many types of egg albumins. Most of them are globular proteins. I think all of them are globular proteins. And then we have long and spindly, which is fibrous protein. Example is collagen. Okay, this one I just got from a good website. They allow me to reproduce this. Beta sheet, maybe you can see the blue beta sheet, and then we have the alpha helix, the green bit. Okay, we combine these two. Now the whole protein is complete, and this protein can work for you for certain function. Well, I do not know what is this protein called, but in terms of structure it is tertiary. Okay, the tertiary structure is held by several bonds and interactions. For instance, the disulfide here, hydrogen bond there, hydrophobic bond there, and then ionic interactions. Alright, so because they are folded, they need something to hold them together, like a rope, to make them stable. Otherwise, they won't be able to stay as they are. If they're not able to maintain the shape, they're not able to function. So the role of these bonds are very important. So if you apply heat or something that can destroy this bond, you will cause what we learn later in the later chapter. You will cause denaturations. Okay, now we are ready with the tertiary becoming quaternary. This is one tertiary protein. This is another tertiary protein. Now, if they come together, into one new protein. Now we are combining 4 different protein structure into one. So this is called a quaternary structure. Okay, it's a complex of 2 or more tertiary structures, or you can call multiple polypeptide subunits that come together to form a larger protein. So between the units, they are not covalently bonded but are electrostatically linked with one another. So you see between these 4 different polypeptides, between them they are not covalently linked but electrostatic interactions are used. It's strong enough to allow the subunits to arrange themselves in specific ways. Example here is hemoglobin. We have 4 totally separate polypeptides arranged in a very specific way, and you're going to learn later on. Maybe you have already known about the roles of hemoglobin to carry these oxygen molecules. If something is wrong with one of these polypeptides, or one of the amino acids in one of these polypeptide chain, this hemoglobin will not be able to function to carry the oxygen. It's going to be a disaster. It's going to be a special types of anemia. Well, don't go to details, enough for now. Anyway, summary is very simple: a complex of 2 or more tertiary structures. Okay, so good. You have covered the protein structure. Basically, is the most basic I can do. This is just a summary. We have learned the hierarchy: primary, secondary, tertiary, and quaternary. You can read all of this later on, but for now, sufficient that we learn about the structure. Next, we learn about the functional properties, because we want to apply the protein in food system. Okay guys, happy learning.